Franklin is a junior research fellow at the Institute for Cross-Disciplinary Engagement at Dartmouth College. He works on topics in the history and philosophy of science, in particular on issues of realism, evidence, theory choice, data, and on understanding the relationship between social and epistemic factors in science. Chemistry and biology provide especially fruitful case studies for his research, and he's going to be contrasting two different case studies from 18th century chemistry. So I look forward to listening to that. Thank you. Is it on to me now? I'll assume so. Okay. Thank you. Thank you for sticking with me here for the last talk. I'm also not sure if that's a good or a bad thing, but thanks to the organizers for making this happen. It evidently took a tremendous amount of effort to make this so successful and productive, and I'm really grateful to be here. I thought I might start by saying that I came to the idea of serendipity and its application to the history and philosophy of science rather recently. And I thought it might be a useful tool for thinking about some of the case studies I've been developing, in particular related to some experiments from the chemical revolution, which is a period that is notoriously difficult to characterize, and that we also say features important chemical discoveries, most famously the discovery of oxygen. And serendipity, since it's meant to tell us something about the discovery, I thought might be a useful way of thinking about this period. If you want a very succinct expression of everything I'm going to say, I think this phrase here, this sentence, does it very nicely. Discovery is seeing what everyone else has seen and thinking what nobody else has thought. So if that's the only slide you see, I would encourage you to see that slide. Although I won't mention big data much during this talk, I think data generally have some core interesting epistemic features in common, regardless of how big they are. And in the past, when data were fewer and easier to manage, we might find simpler cases that help us better understand philosophical problems with data that we face today, even though we now also face new problems, particularly with quantity and with analysis that we did not face previously. In this talk, I'm going to evaluate two claims involving serendipity, one about evidence and data and the other about contingency. The first and primary claim is this, that recognizing unexpected or anomalous data results requires alternative theory, and it's so historically contextual depending on what theories are available at the time. So, and in particular for this project here, the discovery of oxygen by Antoine Lavoisier, which I'll describe more shortly, was serendipitous because he had a theoretical background that allowed him to appreciate anomalous and unexpected data. So having a rival theory available is essential for discovery. The second claim I would like to explore concerns the contingency of controversial revolutions in science, such as the chemical revolution. Serendipity suggests an element of chance, and this jives with a number of interpreters of the chemical revolution, especially since Kuhn in the 60s, who have suggested that the discovery and subsequent adoption of oxygen was not necessary. Some authors even suggest it was ill-advised. Most recently, Hasek Chang has eloquently defended this quite strong position. I think serendipity helps us understand contingency by pointing to the type of historical analysis we should be looking for when we examine controversial changes in science like this. And that's the second claim I would like to explore today. And I say that these are claims I'm going to explore because I think serendipity may prove really fruitful here, but I also have some reservations that I'll discuss towards the end of the talk, and perhaps you can help me better understand how serious those reservations are, and maybe they're not very serious at all. Here's the plan for what I'm going to do. So the main general question is, how can serendipity help us understand revolutionary change and data in science? And I talked a little bit about what that's going to look like. I'm going to have those two claims, those more specific claims about data and about contingency. But to do that, I'm going to need to tell you what I take data to be, and then what I take unexpected data or anomalous data to be, and what makes them unexpected. There are also, I gather, a number of ways of thinking about serendipity, and I'll just clarify how I'm thinking about it. And there might be other fruitful ways of thinking about it, and that would also be very helpful if you wanted to share those with me later. I'm then going to talk about the case study a little bit and contrast those two sets of experiments, as Wendy alluded to, and then try to discuss why I think serendipity might be helpful here. And then I'll return to those reservations I have, and then I will conclude. All right, so let's move on here. So data, I take data to be, for this talk anyway, records of observations or experimental outcomes as they are conceptualized within particular research contexts. As such, they have the potential to serve as evidence. This has rough similarities with how Boggin and Woodward think about data in their account that they developed in the late 80s, but it has a bit more distance from Leonelli's more recent relational account that defines data as evidential objects. Although having said that, there are important differences between what I'm doing and what I think Boggin and Woodward do with data. I don't think we need to worry about the details just now, but I'm happy to talk about this later as well. Okay, so if that's data, I take unexpected data or anomalous data, I'm thinking of this interchangeably, as data that or experimental, records of experimental outcomes that do not fit with what prevalent theory leads us to expect, or even what past experience might lead us to expect. So there are things we have no ready explanation for using the most accepted or obvious theories available. They're puzzles. They're perhaps an example of Kuhnian anomalies that can help prompt revolutions, which is particularly appropriate here. And a crucial question, I think, about unexpected data is who recognizes them as unexpected? For whom are they unexpected, and why are they seen as unexpected? And I think asking this question about why they're unexpected suggests that serendipity might tell us something interesting about them. And this is in particular where my serendipitous journey began, in thinking about unexpected data. And I gather there are a number of ways of thinking about serendipity. I'm in particular thinking of, I believe, analytic serendipity. And I think Fine and Deegan were the first to define it in that way, but Copeland nicely describes it as recognizing the value of the unexpected. And that's that's the idea I'm going to be working with today. And again, thinking about serendipity in that way, there's this question: what is unexpected, and why is it seen as unexpected? There might also be another sense of serendipity at play in what I'm going to talk about. There's a lot of preamble here, but it'll be worth it, because I'm going to be talking about experiments of laboratory work that involves carefully constructed apparatus and carefully constructed results, even if the results are unexpected. So serendipity might not just be this passive valuing of the unexpected. There's also a sense in which there's something that is made, even if it's not expected what it is we're going to make. Okay. I'm just going to give a very quick overview of this period. This might be familiar to some of you, especially since this is an incredibly overwrought period of time that historians and philosophers have found so very fascinating. But maybe even if this is familiar to you, you'll find how I think about it helpful for the rest of the talk. So this period occurred at the end of the 18th century within chemistry, and it involved a number of important and quite dramatic changes to the field of chemistry. Perhaps most famously, this period saw Antoine Lavoisier introduce oxygen, and we often say today that he discovered oxygen. And in the process, they abandoned using the term phlogiston and thinking that there was this substance phlogiston, which I'll talk more about in a moment. And it also saw chemists start to use weight or gravimetrics more consistently and more precisely. Indeed, the origins of the conservation of mass lie within this period, the idea that for any reaction, the mass going into it has to be the same as the mass going out of it. You don't have mass simply appearing and disappearing spontaneously. Now, phlogiston was thought to be a substance that combines with rust to form metals, such as this zinc powder here. Powdered metals were a common experimental ingredient during this period. But not only that, it was also something that was emitted when materials combust. So if you burn something, there are these fumes that come out, and it was thought that that was phlogiston. And there was a lot of uncertainty about what precisely phlogiston was and whether it could be isolated. One possibility was that it was the same as what they called inflammable air, which you can see very nicely lifting this balloon and carrying this little vessel across the hillside. And just a quick terminology thing: air is roughly synonymous with gas. I suppose if you think air, then think of a gas. And very roughly, this use of phlogiston is opposite to our current thinking. This might be a useful way of thinking about it anyway, if we get lost in the weeds here. And that is that if you're a phlogiston chemist, you think that that metals are a compound formed of a rust or a calx, as they are called. I'll use those interchangeably, rusts and calx. And that during combustion, something is given off. And this is the opposite of today. Today, we think that metals are actually the simple substance and rusts are the compounds. They're formed of metals and an oxygen, they're an oxide. And we think that in combustion, oxygen binds to something. I mean, of course, flames are often emitted if smoke comes off, but not always. The essential feature of combustion is that oxygen binds to something. And so this is opposite to what they seem to think. And there were lots of other important things that were at stake here during the late 18th century, such as the composition of water and some other things. But these are some of the essential notions. And nitrous acid is also going to be an important part of this experiment, but you don't need to know too much about that. All right, so Lavoisier, he who discovered oxygen, he began at least as early as 1772 having doubts about using phlogiston, the prevalent theory at the time, to provide explanations for a number of chemical phenomena. But he did not have, at that time, a well-developed alternative. He believed that something must combine with metals to form calxes, and so he was already starting to think that maybe the phlogiston picture had things backwards, right? That the rusts are the compounds and the metals are the simple substances. But he wasn't sure what it was that combined with the metals. Was it the atmosphere? Was it a new air or gas? Was it just a modification of atmospheric air? It was not actually until 1774, so 2 years later, that he started to think that the atmosphere was more complex than a single homogeneous substance. And not until 1777 that he had what seemed to be a coherent, developed, and alternative form of explanation that did not involve phlogiston, but which did involve oxygen. Before this, phlogiston actually featured in his explanations, though often without, we would say now anyway, coherence. So this 5 or 6 year period from 1772 to 1777 was crucial for Lavoisier's intellectual development and for the development of oxygen chemistry, as it was called. And we might say that the discovery of oxygen happened over this period. As others have argued, however, there was not one crucial experiment during this period where oxygen revealed itself to Lavoisier. His theoretical development progressed simultaneously with his posing more precise questions and with his development of the appropriate experimental practice to help answer those questions, which in turn helped him to more fully develop his theoretical views. And you can see here some of the incredible intricacy of his experimental apparatus. You don't worry, I'm not going to talk, I'm going to skip over a lot of the detail here, but it's just incredible, the precision, glass blowing and metallurgy required to make this stuff. I'd like to talk about one of his experiments in particular. He presented the results from it in 1776. So it's after he started to think critically about phlogiston and about coming up with a new style of explanation for metals. But shortly before, he had developed a full alternative, which was about a year later. He does not use the term oxygen during his analysis of this experiment, but he does reference an elastic fluid, which is what he later does call oxygen. For this experiment, I'll just describe it quite briefly, but I'm happy to talk about the details if anyone's curious. So he's interested in metal, and what he does is he dissolves an iron powder in acid, the nitrous acid, to its saturation point. So he's got pure metal powder, he dissolves it in acid, and then he wants to isolate it. So he adds chalk and lime, and it's now a rust or a calx precipitates out of the solution. He washes it in distilled water and he weighs it. He also weighed the starting ingredients. So he weighed the metal and the acid before the reaction, and he weighs the calx after the reaction. And he finds that the calx is heavier than the metal was before being dissolved in the acid. And this is what he concludes. The results of these experiments are, first, that iron dissolved in nitrous acid acquired in particular a remarkable increase of weight. And one reason for thinking that the elastic fluid contributes to this augmentation, so that's what he later calls oxygen, is that it is constantly greater when an earth is employed, saturated with elastic fluids such as chalk, than when an earth is used which has been deprived of it, as lime. So there's a lot going on here, and the language might seem unfamiliar, but the crucial result is that the weight gain in the calx was systematically related to the substance with which the metal was combined in the experiment. For those substances that Lavoisier believed had more elastic fluid, the weight gain was greater than for those substances that did not have the elastic fluid. And so if you want to make sense of why calx is heavier than metal, if you're Lavoisier, you need to posit that something is combining with the metal and making it heavier. Now, this on its own to me does not sound like serendipity. That is, this one experiment and its results are not unexpected and not unlooked for in a way that suggests a discovery of a serendipitous kind. This is because Lavoisier was looking for something, even if he was not sure what the results would be, and he was already starting to use alternative styles of explanation. But I think as part of the broader context of Lavoisier's work, we might think of that broader project as serendipitous. Because even though the weight gain of the calx was not unexpected, Lavoisier is in part showing us that that fact, that weight gain, should be unaccepted and should seem anomalous and strange, unless there is an elastic fluid involved. In other words, his experiment suggests that we need an explanation here. There's something funny going on. And the existing prevalent theoretical structures we have available are not giving us satisfactory answers to those. So I said that this weight gain of the calx stood in need of explanation. Lavoisier was nearly alone in believing this at first, because the weight gain of the calx was actually not remarkable to most chemists at the time. Indeed, Lavoisier is partly unique in finding it something worth studying, as we'll see in a moment. And I'm going to show that by contrasting what he's doing with an experiment by Henry Cavendish, who was doing very similar work, but without knowledge of Lavoisier. In fact, Lavoisier didn't know of his work either. It was an independent project, as far as we now can tell. And Cavendish did not find the weight gain of calxes remarkable. Indeed, he did not address it at all. Henry Cavendish worked on a wide range of physical phenomena, and most of his scientific work was actually not spent on what we might call chemical studies or chemistry. But he did do some work, and it was remarkable work in a number of ways. And several years before Lavoisier's work, in 1766, so 10 years roughly before Lavoisier presented his results, Cavendish worked on metals and factitious heirs, as he called them. And heirs are what we now call gases that become trapped, fixed, or bound in some way in a solid form. So they start out in the atmosphere around us and can be bound up. And here's what he did. He and you can see this. This is in particular figure 1. Don't worry too much about the details. I'll be brief. But what he does here is he has a bottle, and he puts into it a mixture of acids and metals, and he plugs a glass tube into that bottle. And on the other end of the glass tube, he attaches an inverted bottle filled with water. And then key parts of the system are submerged underwater. And so parts of it are airtight. And what he's able to do is he's able to mix things in the first bottle. Any gases or airs that are produced flow along the tube into the second bottle, and they displace water. And based on how much water is displaced, he can figure out how much is produced by his reaction. So with this, he investigates the reactions of 3 metals with 3 acids, and he does each one metal, one acid at a time separately. And generally what he found was that inflammable air, as he called it, was produced. And he believed that was oxygen. Recall from a few slides ago that the balloon was filled with inflammable air. And he's quite remarkable for thinking that it is phlogiston, that they're the same substance. And he doesn't say how he knows that it's this gas, but in other experiments, he uses a candle and he ignites the inflammable air, and the poof, it shows him that that's what it is. Now, like Lavoisier, Cavendish has mixed acids and metals, and he has weighed various parts of his experiments, but he has not weighed all the starting ingredients, as Lavoisier has done. So he has no way to compare the weight of the metal and the calx. Because, of course, upon putting the metal and the acid into the first bottle, the result is this sort of murky liquid and a calx. So he gets the same sort of products as Lavoisier, but he doesn't have a way of addressing the weight gain. And he doesn't do this because he takes it for granted that metals are the complex substance and calxes are the simple one. In other words, he takes phlogiston theory for granted. That's not what he's interested in doing with this experiment. The weight gain of calxes is not interesting. It is not worth collecting data on it. It's not worth experimenting with it. It's just not of interest to him. And this is not remarkable. It has been known since Ernst Stahl, at the beginning of the 18th century, and the one who introduced the term phlogiston, that calxes are heavier than metals. And generally, this was not a troublesome fact for anyone. It wasn't something that Lavoisier discovered, and Cavendish certainly would have been aware of it, in part, and that's probably why he didn't bother to weigh his materials. So the entire history of phlogiston was tangled up with this funny feature about weight, and it was not unexpected, and it could be, to many, easily explained. A number of different people studying substances containing phlogiston drew what seemed to them the obvious conclusion, when explanation was needed at all, and typically it was not. Joseph Black, for example, thought that phlogiston must have levity, and so when it departed a substance, the phlogiston left the substance heavier than before. Most people did not feel that way. He was unique in that. So the data for the early students of chemistry were not anomalous. Existing theoretical structures provided what was to them an adequate explanation to the extent that an explanation was needed. The heaviness of calxes was not a problem. The data were not unexpected. So this suggests to me that how strongly one believed in phlogiston chemistry determined, in part, what data were unexpected. and whether alternative forms of explanation were needed, and whether one had to introduce the term oxygen at all. Also important here, though, of course, is how important and how serious one took the idea that the complexity of a substance was connected to its weight. Was the greater weight of something an indication that more substance was involved, and hence that it's perhaps a compound or a complex substance? If one gives a positive answer to this question, then phlogiston chemistry is going to seem unsatisfactory, and rival views will seem better, even if they are not fully developed. This was, of course, what happened for Lavoisier. I think we can now answer some of the, don't need to read that, some of the questions I started with. So one of those questions was what counts as unexpected, and who does the counting? Who counts as unexpected? Who thinks that? And this contrast here suggests to me that something is unexpected, that the data from an experiment, say, are unexpected, when there is an alternative theory that gives a more satisfactory explanation than the older theory or the more prevalent theory, phlogiston in this case. So the heaviness of the calx was not a problem for phlogiston chemists, but it also was not an asset. It was uninteresting. It had to be uninteresting. And for oxygen chemists, the heaviness of a calx is an asset because they can give a very parsimonious explanation, parsimonious, that is, with respect to weight. They don't have to posit levity or anything else. So the weight gain of a calx is unexpected, we might say, in retrospect, when we have rival theories. And one of those theories gives a good explanation while the other offers no explanation or is silent on the matter. And I'd like to return then to this question of serendipity. What does serendipity do for our interpretation of this period? I've talked a little bit already about how Lavoisier's doubts about phlogiston allowed him to think of his results as unexpected and as in need of explanation in a way that others, his contemporaries, did not. And that, to me, suggests an element of serendipity. But I don't think that's the only sense in which serendipity is applicable here. As a retrospective description of discovery, I think it also draws attention to the way in which we think about doing history. After all, we are looking back and trying to make sense of how it could be that oxygen chemistry emerged based on the theories available and the experiments that were possible. In this light, it is striking how long thinkers who studied substances were able to provide chemical explanations without appealing to oxygen. Indeed, for most of history, oxygen was not a concept at all, and explanations of metals, of combination, of decomposition, did not require it and did not seem deficient for not using it. Therefore, it is remarkable that Lavoisier posited oxygen at all. And I do not think we do violence to the concept of serendipity when we say that the emergence of oxygen chemistry was serendipitous. Indeed, Lavoisier was not forced to develop his new system. There were alternative modes of explanation available, and they were widely accepted. And yet, for Lavoisier in particular, there was a deep need for theoretical revision, and driving that need were theoretical inadequacies that arose when the prevailing theories confronted unexpected data, or data that in particular seemed unexpected when natural philosophers began to think weight should be used as part of a more consistent experimental practice, and when they had other theories available. So in thinking about this period in terms of serendipity, I think we draw attention to the feeling of contingency that we get when we examine past science. Why is this important? Partly, it is so that we can do justice to past scientists, as many historians have urged us to do, and others. We can do justice, for example, to phlogiston chemists by showing the strength and coherence of their views. But of course, addressing that feeling of contingency just isn't about giving phlogiston chemists their dues. It also shows that to make sense of historical events, that is to understand how and why seemingly chancy episodes went the way they did, we need a story about how and why events unfolded in one way rather than in another. And it's not just any story. It's a story that involves and must involve evidence, and epistemology. To say that things could have happened differently is to imply strongly that there were reasons why they did not turn out differently, and that those reasons were important to past scientists. And so we might find them important to us today. I think there are a number of questions I still have about, though, applying serendipity to this period. One, for instance, is whether it's actually better described as pseudo-serendipity, so perhaps presented as a case of miraculous discovery when in fact it was not so unexpected. And in favor of this view is perhaps the fact that there isn't any single experiment that seemed very serendipitous. There was no eureka moment. It was accumulating experimental results, incremental theoretical development, and an increasing willingness to abandon phlogiston that all were required for the discovery of oxygen. I mean, having said that, it is, I think, the case that Lavoisier did not set out to reject phlogiston in 1772 when he started on this this journey that culminated in the discovery of oxygen, and he doesn't set out to develop a new theory. So even though he came to want to do both, I think if you were Lavoisier in 1772 looking forward, you would not have been able to expect what was going to happen in 1775. And maybe that seems trivial, I'm not sure. So I think there is this this issue with thinking about serendipity here. And then there's also this fact that it was well known that phlogiston had to have levity, or you had to not find it an interesting fact, or maybe you had to come up with some other sort of explanation for it. But there wasn't, people knew calxes were heavier, and it just wasn't addressed. So maybe it doesn't seem very surprising that oxygen chemistry was developed in light of this. That might be another worry one would have here. So I think more generally, we might wonder if specific moments that are surprising, unexpected, unlooked for are essential conditions for serendipity, then there's perhaps little to be gained from using it to understand the chemical revolution. And there might, so it's, I think, quite a strict notion of serendipity, and it might be that that's the one that we should use. But if a looser notion is acceptable, then I think it might be interesting to think about it because of this notion of unexpected data and because of contingency. So maybe I'll just quickly review what we've done here today. So I've suggested that what experimental results seem unexpected depend in part on what theoretical explanations are available. Lavoisier was able to find the weight gain of calx interesting and worth explanation, and kind of unexpected in light of phlogiston theory, because he had another way of thinking about it already, even though it wasn't fully developed. And I think, so that's, I think, suggests that there's maybe an element of serendipity there. Serendipity, I think, also addresses the sense we may have that past events are contingent. I'm not saying specifically that they are contingent, but it helps us think about what kind of historical story we want to tell. And I think we need to tell, at the very least, an epistemic story. That does not, of course, preclude other types of story that we would like to tell, or that we might need to tell for other reasons. But certainly, I think to make sense of this event and understand why it happened, we need an epistemic story that's going to appeal to evidence, to data, and to experiment. Here's a very, very selective list of references. I'm happy to share more if anyone's interested. And that's all I have for today. Thank you very much for your time and for your attention.